Measure Theory series. This class asks the question, when are observations dependent? In fact, what is an observation and how is this evident in the data or in the data generating process? One of the examples given in the previous video of a complex measurable space was assigning a patient drawn from an equal probability sample to a randomly selected treatment. Another example was going out and collecting 5 people for a study. This second example is the kind of complex measurable space we will discuss now. Here you have a population of 25 people. Say you want a sample of 3 people. You will get these 3 people one at a time, so there will be 3 draws from the population of 25. And for each draw there is a measurable space. For each draw, that is a round in which you engage the data generating process. And each round of the data generating process is represented by a measurable space. So this is a measurable space for the first round of the data generating process. The outcome set contains all the people you could get on the first round of the data generating process. And the events set is, of course, the sigma algebra. With equal probability, you go in and grab a person, record information about them, and after that first round, you need to get the second person. So now you have another measurable space. And then you engage the second round, and you get your second person. And after that second round of the data generating process, you have another measurable space in order to get the third and final person. And then you engage the third round, and you get your third person. You can have a complex measurable space from these 3 simple measurable spaces. You engaged the data generating process 3 times, and now you have a sample size of 3. So let's say you want to ask, are these observations independent or dependent? First, you have to be sure about what you are asking. Are you asking, are Fred and Sophia independent or dependent? Are Sophia and Akbar independent or dependent? If so, then these are not questions about observations. Fred, Sophia, and Akbar are not observations. They are the people in your sample. If, on the other hand, you are asking, is the outcome that could possibly occur on the second round of engaging the data generating process independent or dependent of the outcome that could possibly occur on the first round of engaging the data generating process? Then you are asking questions about observations that can be dependent or independent. Let me say that another way. If you're asking, is the probability of which person is drawn on the second round of the data generating process influenced by who was grabbed on the first round of the data generating process, then you are asking questions about observations, and those observations can be dependent or independent. Dependence and independence has to do with probabilities. The outcome that could occur on the first round of engaging the data generating process is an observation. It is an observation because it has a distribution. The person Fred, who we got on the first round, does not have a distribution. Fred is just a person, a single data point. But when we're modeling uncertainty about the data generating process, when we are modeling uncertainty about getting a person in the sample by engaging the process, that has a distribution, and that is an observation. Probabilities are associated with how you get the data. Probabilities are modeling the process. So let's look at the process of getting someone. Let's look at a data generating process. Say we want information about children. We want to engage the data generating process to capture the first child, and we are prepared here with a table to record the information. So the children are running around the playground, And this row is associated with the first observation. It has many possibilities. It has a distribution. When we go into the playground, we're able to pluck a child from the playground at random with equal probability. This child, Fred, gives us some information, and we thank him and throw him back into the playground, and we record that data into the table. This data is not an observation. Once Fred is captured, we have a favorite color of green and a favorite flavor of chocolate and a 10-year-old, all with the probability of 1. There's no distribution of possible values for these attributes. You could have gotten any one of the children, which means this spot in the table, this row, is what could have taken on a lot of different values. This row, before a data point is obtained, is associated with a distribution of possible outcomes. Thus, this row is associated with an observation. But once you have data, you have exact information, and you no longer have a distribution. Fred, the 10-year-old, and his attributes are data points, not an observation. Okay, now after we throw him back into the playground where the children are still running around and we still have that table, we're prepared to engage the data generating process to capture the second child. This row is associated with the second observation. It has many possibilities. It has a distribution. We again pluck a second child from the playground at random with equal probability. This child, Sophia, gives us some information. We thank her and throw her back into the playground. Record the data into the table. The engagement of the data generating process on the first round is the first observation. The engagement of the data generating process on the second round is the second observation. An appropriate discussion of independence or dependence is whether or not the distribution of favorite color in the second round is related to the distribution of favorite color in the first round of the data generating process. But Fred likes green or Sophia likes purple. That has no notion of dependence or independence. These are simply data. So this is a process where you have sampling with replacement because we threw Fred and Sophia back into the playground. We got Fred on the first round. How does that affect who we get on the second round? When we got Fred with the equal probability sampling, there was a 1 in 25 chance of getting some child. We threw him back in. Is there still a 1 in 25 chance of getting some child on the second round? Well, that depends. If Fred goes back into the playground and continues to run around with the other children, then yes, on the second round there still is a 1 in 25 chance of getting some child, and the observations would be independent. But if on the second round Fred remembers us, and when he sees us coming in for the second round, runs away from us, then no, now there is a 1 in 24 chance of getting a child, and the observations are dependent. Also, if Fred runs away screaming, and the other children get scared and also start to run away from us, and it becomes hard to capture any of the speedy children, then also no, the observations are dependent. What about a process where you have sampling without replacement? When we do not throw Sophia and Fred back into the playground. Well, we got Fred on the first round. How does that now affect who we get on the second round? When we got Fred with equal probability, there was a 1 in 25 chance. If we keep Fred out of the population, and then in the second round, the sampling probability associated with Fred is now 0. And with equal probability sampling, there's now only a 1 in 24 chance of getting some child. Since the probabilities associated have changed from the first round to the second round, these observations are not independent. The first and second observations are dependent. So that was sampling with replacement and sampling without replacement. There is another strategy called nested sampling or cluster sampling. And we can ask the same question. Are the observations dependent? So given this data, notice that some of the patients here have the same physician. Can we tell if the observations are dependent or independent? Well, that is a trick question because the data alone cannot tell us. Only knowing the data generating process can tell us if observations are dependent or independent. Here's one potential data generating process that could have manifested that data. At the Acme and Boyles Dermatology Clinic, you at random sample patients with replacement. And this is how. 1. Get a patient from a random name generator. 2. Record their age, height, and weight and physician. 3. Throw them back into the patient pool. In other words, don't eliminate their name from the random name generator for the next round. The data generating process looks like this. You get a patient, record their information, throw them back. You get another patient, record their information, throw them back, and you finally get a sample of 6. Is this a nested sampling data generating process? Well, it is not, because the patients that share the same physician do so coincidentally. So the question was, are these observations independent or dependent? Let's look at this table. For the first observation, what is the probability of getting a particular patient? For the second observation, now that the first observation was realized, what is the probability of getting a particular patient? Did the distribution change between observation 1 and observation 2? Let's look at it a different way. This will help answer that question. The physicians are listed from 1 to 4 at the head of the rows. The patients are listed from 1 to 8 at the head of the columns. These patients all stick with their physicians and they don't see any other physician. Listed in each cell are the probabilities of obtaining a patient participant for each physician-patient pair. The probability is determined by the data generating process. This table represents the probabilities associated with the first observation. The cells of patients with other physicians, not their physician, have probabilities of 0 attached to them. So these probabilities are associated with the first observation under the data generating process I just described. Now I'm about to show you the probabilities associated with the second observation under the data generating process I just described. Check it out. Observation 2. What changed? Observation 1, observation 2. Observation 1, observation 2. Nothing changed. The second observation is not dependent on the first observation because of the data generating process I described. The two observations are independent. Now let's look at another data generating process. Here's another data generating process that could also have produced the data we saw in the table. First, randomly sample physicians, then randomly sample 3 patients from that physician with replacement. Replace the patients and then replace the physician and repeat. So there's random sampling and replacement at each level, at the physician level and the patient level. Is this a nested sampling data generating process? In this case, it is, because the patients that share the same physician do so not coincidentally. They share the same physician as part of the design. Here you can see the pools of physicians and patients. They are color-coded so you can see which patients belong to which physicians. This is what the data generating process looks like. You randomly select a physician from the population of physicians, then randomly select a patient of that physician, record their information, then throw the patient back into the pool of patients. That is sampling with replacement of the patients. Select another patient of that physician, record their information, and replace. Then select the third and final patient of that physician, record their information, and replace. Then finally, after sampling 3 patients from that first physician, you throw the physician back into the physician pool, thereby sampling the physicians with replacement. And then you select at random another physician, select a patient of that physician, record their information, replace, and you do that 3 times. And finally, after sampling 3 patients from the second physician, you throw the physician back into the physician pool. Are these observations independent or dependent? Let's look at this table for the first observation. What is the probability of getting any particular patient for the second observation? Now that the first observation was realized, what is the probability of getting any particular patient? Did the distribution change between observation 1 and observation 2? Well, let's look at it another way. This is a table of patients and physicians. Listed are the probabilities for each physician-patient pair. These are the probabilities determined by the data generating process. For the first observation, these probabilities are associated with the first observation under the data generating process I just described. Now I'm about to show you the probabilities associated with the second observation under the new data generating process. Check it out. What changed? Observation 1, observation 2. Observation 1, observation 2. Are the observations independent or dependent? They are dependent. Why? Because the probability of obtaining a participant in the second observation is determined by the participant obtained in the first observation. So now I'm about to show you the probabilities associated with the fourth observation. But real quick, let me make sure it's clear why observation 1 and 2 change. Once you get a patient in observation 1, you stay with that patient's physician to get the next patient. So if a patient was selected from a physician 1, then the only options are these 3 patients that belong to physician 1. All right, let's look at observation 4. What changed? Observation 2 and observation 4 are very different. Well, for the first 3 observations, we got patients from the same physician, but in the fourth observation, you throw the patient and the physician back into the pool, and now it's just like observation 1, where you're starting from scratch and you pick a physician. So observation 4 looks exactly like observation 1, exactly like what we started with. Are the observations independent or dependent? Well, there is dependence within clusters, but independence across clusters. So there's the dependence within clusters you can see between observation 1 and observation 2, and the independence across clusters is what you see between observation 1 and observation 4. The next 2 slides just show that same table with 3 more observations. This one is sorted by physician, and this one is sorted by name of patient in alphabetical order? Can you tell the clusters? Are there two clusters clustered on the physicians Gupta and Whale? Can you tell which patients are in the same nest? Having the same physician does not imply being in the same nest. Because you threw the physician back, you sampled physicians with replacement. So that physician could have been obtained a second time on another round of the data generating process in which you select among the physicians. So if there were 6 patients with a particular physician, like there are here with the physician Whale, how do you know which patients are clustered together? Presented with only the data on hand, you don't know. You would have to add a variable that was an indicator of cluster. You essentially have to know the data generating process in order to know the clustering. The data cannot tell you unless you provide a way for someone to understand the process you went through to obtain the data. The best scientific way to go about getting data is to design a process, because then you know what the data generating process is. And you have to know the data generating process to know what you are modeling with the probabilities. But instead of designing a process, the same data could simply be handed to you. You want information about patients, and the receptionist says, "Here are the people who showed up at the clinic yesterday." There was no process that they or you undertook to create the data. There was no design. But what do you do with the data if you do not know how the data is generated? How do you model the probabilities? So here's the scenario. There are 2 physicians that work at the clinic, and their shifts do not overlap. You have people in the community and the time of day. So these are the people in the community. This is the time of day. Here's the urgent care clinic with the 2 physicians whose shifts do not overlap. This is your complex outcome set. Suppose what nature does is randomly and with replacement select an individual and a time independently. Nature then strikes that person with lightning, and they have to go to the urgent care clinic. And they show up at the preordained time. So this is the first observation, independent of the second observation. Nature samples with replacement and samples people with replacement and samples time with replacement for each observation. But this is just one scenario for what the natural design process might be. That could have generated the data set that the receptionist handed us. When you create a scenario to try and depict some natural design, you want to ask yourself, how likely or plausible is this scenario? Because you really don't know what happened. You need to arrive at a reasonable model for what nature is doing in order to understand dependence and independence in your data. So this scenario I created could be done 2 ways. One, sometime at the beginning of the universe, nature created this table for this day. One person was selected at random. One time slot for that person was selected at random. So that person will have to go to the clinic at that time, and then the person and the time slot were placed into their respective pools, and these 3 steps are repeated for each subsequent observation. So for observations 1, 2, and 3, none of the observations are dependent on the previous observation. Each of these 3 observations are associated with this same probability structure because the data generating process is designed this way. Let's discuss a second data generating process in which one person was selected at random and a time slot selected at random. Then a second person is chosen at random and a second time slot selected at random. But the second time slot is only selected at random from the time slots available after the previously chosen time slot. Let's see what that looks like. We engage the data generating process for observation 1 and we get person 3, who has to go to the clinic at time period 2. So we have person 3, time period 2. So what does that mean for observation 2? For observation 2, it means whoever gets picked, they have to go to the clinic at some point in time after time period 2. And this table reflects that stipulation, which indicates dependence. The time period probability of observation 2 depends on observation 1. So we engage the data generating process and we get person 2 at time period 5, which means that observation 3 can only obtain time periods after time period 5. And that means observation 3 is dependent on observation 2. I hope this helps you understand what an observation is and when observations are dependent, and I thank you for watching this video. Feel free to like, subscribe, and comment, and the next video we're going to talk about what makes your variables random.